Section 19C, kinematics. So we're talking about, let's go to our next slide here and I'll come back to this. We're talking about displacement function, velocity function, and acceleration function. So if we recall back to differentiation, if we have a displacement function called s of t and we differentiate it, we end up with a velocity function. We could also call that velocity function s dash t, or we could call it ds dt. Okay, if we then take that velocity function and differentiate it, we end up with an acceleration function. We could also call that acceleration function the first derivative of the velocity function, or dv dt, or we could call it the second derivative of the displacement function, with either of those symbols, notations. All right, now we're looking at integration. So since differentiation and integration are basically opposite operations of each other, we can now take this acceleration function, integrate it to get a velocity function. Likewise, we can take that velocity function, integrate it to get a displacement function. Now when we do this, we have some other notation that we then can call these functions. We can actually call this velocity function the integral of the acceleration function, and that's with respect to time, so dt. We could also call this displacement function the integral of the velocity function. So there's a couple more bits of notation that we could call this displacement function, velocity function, and acceleration function. Okay, this is going to be fun. So if we look back here at our first slide, kinematics. So we know we're dealing with displacement, velocity, acceleration. When we think about displacement, though, we also can think about distances. Okay, now let's remember the difference between, I'll just go to the second slide again so I can write something down here. Let's remember the difference between displacement and distance. Okay, so displacement, and I'll call it total distance traveled. All right, so for example, if we are in Windsor and we travel to Halifax, and then we travel back from Halifax to Windsor, our displacement is 0. Okay, but the total distance traveled is not 0, of course. It's about 65 kilometers to Halifax and 65 kilometers back. So the total distance is 130 kilometers. Okay, so hopefully this can show you the difference between displacement and distance traveled. Distance traveled, absolutely fine. Displacement is the difference between your starting point and your ending point, which in this case is 0. All right, so distances from velocity graphs. So if we have a velocity graph looks like this. It means that we have speed along our y-axis and time along our x-axis. Okay, so this is a velocity graph. If we have a velocity graph where we are going a constant speed of 60 kilometers an hour, we could draw that on here, okay, for 15 minutes. So that would be from 0 to 15 minutes, quarter of an hour, and that's what that graph would look like. We can then calculate the total distance traveled based on the area under that curve. So the total distance traveled in those 15 minutes is this area under this curve. So we can calculate that using geometry. We know here that this side is 60 and this side is 1/4. And when we multiply that length times width, we get 15 kilometers. Okay. Another way, now that we know about calculus and integration, another way of calculating that area under the curve is taking the integral of that velocity function from 0 time to 1/4 of an hour. Okay, and time is in hours in this case. This is the function, the velocity function is just 60 kilometers an hour, dt, constant. So that means that when we integrate that, it'll be 60x. From 0 to 1/4. So 60 times 1/4, subtract 60 times 0, which is 15. Okay, and that is still kilometers. Okay, now suppose the speed decreases at a constant rate. So looking at this second example, the speed decreases at a constant rate so that the car initially is traveling at 60. So again, we can draw this. The initial speed is 60. Velocity graph is speed on the y-axis, time on the x-axis. Initial velocity is 60, and it stops in 6 minutes. 6 minutes is 1/10 of an hour. Okay, so here's 1/10. Stop means its velocity is 0. So there is our graph. Again, we can calculate the distance traveled based on this area under the curve. This is 1/2 base times height. We could do it geometrically, which would be 60, 1/10, triangle, 1/2 base times height, and this would be our answer, 3 kilometers. Okay, but can we do this with integration and calculus? Yes, we can. It's the integral of the velocity function from 0 to 1/10. This time the velocity function is, we need to know what that function is. So in other words, we need to know the equation of this line. We can do that. It's a straight line. So y equals mx plus b. We need to calculate the slope, which is, this point here is 1/10 and 0. This point up here is 0 and 60. So we can calculate that slope, y2 minus y1 over x2 minus x1, going back to grade 8 and 9 geometry, coordinate geometry. So we have 0 minus 60 over 1/10 minus 0. So this is like multiplying by 10. So negative 600. So that's the slope. So y equals negative 600x plus b. Plug in one of these points. I'll choose this one, 0, 60. So 60 equals, so b is 60. I guess we could see that from our graph anyway, because that's the y-intercept. So our equation then is y equals negative 600x plus 60. Okay, so that's the function that goes in here. Negative 600x plus 60 dt. All right, so then we can integrate that. That will equal negative 600, increase the exponent, and divide by that number, plus 60x from 0 to 1/10. And as you can see, this is actually a lot longer than just doing it geometrically, but just showing the point that we can do this. This would be negative 300x squared plus 60x from 0 to 1/10 minus 300. 1/10 squared plus 60, 1/10, and the other, plugging in the 0 is just going to subtract 0. So minus 300 over 100, that's negative 3. And this is 60 over 10, which is 6. And our answer is 3 kilometers. Okay, so that was a long, grueling way of doing it, but just showing that yes, we can do that. All right, so for a velocity time function, we've discovered that if the velocity is above the greater than or equal to 0, in other words, it occurs above the x-axis in this case. Okay, so here's our function, new function that we're looking at. We're looking between time 1 and time 2. We can figure out that distance traveled from this formula, and we just did that back in the previous slide. For a velocity time function that is less than or equal to 0, in other words, it occurs below the x-axis, so this one occurs below the x-axis, we need to use this formula. It's the exact same formula with a negative sign out in front of there, which we already talked about in earlier videos because this is underneath the x-axis, so we need to add that negative sign to our formula. Let's look at some examples. Example 7, velocity time graph for a train journey is illustrated in the graph alongside. Find the total distance traveled by the train. Okay, so in this case, we do not know the function. Okay, so we actually do need to calculate the area under this function, and we can do that geometrically. So they've just broken this up into 1, 2, 3, 4, 5 sections and used geometry to calculate those areas and added them all up. I won't go through that entire thing. Pretty straightforward. Displacement and velocity functions. Okay, so before we're talking about total distance, okay, so up here on this side, we're talking about distance traveled. Now we're talking about displacement. If we're looking at displacement, we need to look at, again, it's the integral function of the velocity, s of t2 subtract s of t1. So you'll notice that this displacement function formula looks exactly like the one that we looked at up above here for distance traveled. The reason for that is because up here we looked at the distance traveled. This velocity is always above 0, so it does not cross the x-axis ever. No change in direction. And this one here, this second example, the entire time it's below 0, so below the x-axis. It doesn't cross the x-axis, so no change in direction. So if there's no change in direction, then the distance traveled and the displacement should be equal, will be equal. Okay, so for example, no change in direction. We just go from Windsor to Halifax. That's it. Windsor to Halifax. And stay there, no change in direction. So the displacement is 65 kilometers, and the distance traveled is also 65 kilometers. So back here then, displacement then, we can just take the end point, substitute it in, subtract it from the starting point, and substitute that in. All right, distance traveled though, if we have some changes in direction. So let's follow these steps. Total distance traveled. To find the total distance traveled given a velocity function, so again we're going to be thinking it's a velocity function or the derivative of the displacement function. We're looking from this time interval, so any time interval from t1 to t2. Step 1 is going to be draw a sign diagram for that velocity function so we can determine the changes in direction. And those changes in direction occur when crossing the x-axis. Okay, so if you think about that, the velocity, if you're going from negative velocity to positive velocity, we would be changing direction. And if we're going from positive velocity to negative velocity, we would be changing direction. And that would mean crossing the x-axis. Okay, step 2. determine the displacement function by integrating. And make sure you include that c, the constant of integration. Step 3, we then need to calculate a few numbers. We need to calculate what the starting displacement is. We need to calculate the end displacement. We also need to calculate the displacement each time of a direction change. And we will get that direction change from our sign diagram. Now, step 4, draw a motion diagram. And step 5, from the motion diagram, calculate the total distance traveled. Using technology, and we've looked at this before as well, using technology we can just use this in our calculator. Make sure we use these absolute value symbols so that it will add all of the areas, whether they're underneath the x-axis or above the x-axis. Here is a good box of information, a summary in the textbook on page 486. And similar to the one that I drew when we were recalling,